Bricks are one of the oldest and most widely used building materials in the world. Making them is a process that begins in the ground and ends with a product strong enough to support a multi-story building. And it happens on an industrial scale that most people never see. The main ingredient in a clay brick is, as the name suggests, clay. There are three principal types used in brick manufacturing. Surface clays are found near the top of the earth, the most accessible and most widely used. Shales are clays that have been subjected to extreme underground pressure over millions of years, compressing them into a denser, more slate-like material. Fire clays are mined at greater depths and have refractory qualities that make them resistant to very high temperatures. All three share a common chemical foundation, alumina and silica, combined with metallic oxides that influence the final appearance of the finished brick. The clay is extracted from open-cut quarries using heavy excavation equipment, bulldozers and mechanical shovels working through deposits that may be many meters deep. Once extracted, the raw material is transported to the brick factory, where the first task is to break it down into something workable. The clay arrives at the factory in large, irregular lumps. It is fed into a primary crusher, which reduces the material to smaller pieces. From there, it passes through grinding mills, roller mills or hammer mills, working the material repeatedly until the particle size is fine and consistent. The ground clay then passes over a vibrating screen. Material that has reached the right fineness moves through to the next stage. Anything too coarse is returned to the grinder. The process is continuous, and nothing is wasted. What emerges is a fine, dry powder, uniform in texture, free of large stones or impurities, and ready to be shaped. The finely ground clay is fed into a machine called the pug mill, a large mixing chamber fitted with one or two rotating shafts armed with heavy blades. The pug mill does two things. First, it introduces water into the clay in a controlled amount, transforming the dry powder into a plastic, workable mass with the consistency needed for shaping. Second, it mixes the material thoroughly, ensuring that the water is evenly distributed and that any remaining pockets of dry material are eliminated. This is also the point at which additives are introduced. Small amounts of manganese compounds adjust the color of the finished brick. Barium carbonate improves the brick's resistance to chemical weathering. Sand or grog, pre-ground, pre-fired material from previous production runs, may be added to improve the working properties of specific clay types. Each factory's formula is tailored to the clay it is processing and the type of brick it produces. What leaves the pug mill is a dense, uniform column of prepared clay, the same material in chemistry and structure as what went in, but transformed in physical character. It is now soft enough to be forced through a die, firm enough to hold its shape after cutting, and consistent enough to produce identical bricks in the thousands. From the pug mill, the prepared clay enters the extruder. The extruder applies considerable pressure to force the clay through a shaped die, a precisely machined opening that gives the clay its rectangular cross-section and determines the final dimensions of the brick. What emerges from the die is a continuous, smooth column of clay moving forward on a cutting table. Built into the die are steel pins. As the clay column passes through, these pins create rows of uniform holes running the full depth of each brick. These perforations reduce the volume of clay needed for each unit, lowering both material costs and the weight of the finished brick. They also improve thermal insulation by trapping air within the wall structure and provide a better mechanical key for the mortar when the bricks are laid. The perforated clay brick is not a variation. It is the standard product of the extrusion process. The moving column of perforated clay passes over a cutting table where a frame of tightly spaced wires descends through it in a single, clean motion, producing 8, 10, or 12 individual bricks simultaneously, each one cut to exactly the same length in a fraction of a second. The result is a row of freshly formed bricks, dimensionally identical, structurally consistent, moving away from the cutter on the production line. These are called green bricks. At this point, they are still clay, soft enough to be marked with a fingernail, with no structural strength whatsoever. Everything that makes a brick happens later, in the kiln. The green bricks are loaded onto kiln cars and moved into a tunnel dryer. A brick that enters a kiln while still carrying significant moisture will crack or fracture as the water trapped inside rapidly expands under heat. The drying stage exists to prevent exactly this. Inside the dryer, warm air circulates around and through the bricks for up to 48 hours, drawing the moisture out gradually and evenly. The heat used is not wasted. It is drawn directly from the cooling end of the tunnel kiln, recycling energy that would otherwise be lost. When the bricks emerge from the dryer, they are lighter, slightly paler, and ready for firing, but they remain fragile. The transformation that gives a brick its strength requires temperatures that no dryer can reach The tunnel kiln is the defining machine of brick manufacturing. It is a long, insulated structure. Some kilns extend for over 100 meters, through which the loaded kiln cars move continuously, pushed forward at a rate precisely calculated for the material being fired. Inside the kiln, the bricks pass through 3 distinct temperature zones. The first is the preheating zone. As the kiln cars enter, the bricks are brought up to temperature slowly and gradually over several hours. Pushing the temperature up too quickly would cause the bricks to crack from thermal shock. The energy used here comes from the far end of the kiln, heat recycled forward through the airflow system, which makes the tunnel kiln one of the more thermally efficient processes in heavy manufacturing. The second zone is the firing zone. Here, the temperature reaches between 900 and 1,100 degrees Celsius, and the fundamental transformation of the brick takes place. At these temperatures, the minerals within the clay undergo a process called vitrification. The silica and alumina particles begin to melt very slightly at their surfaces and fuse together to form a glass-like bond between particles. The clay's plasticity is permanently destroyed. Its structure becomes rigid, dense, and durable. A brick that entered the kiln as a fragile, dry clay form will emerge from this zone as a load-bearing building material. The color of the finished brick is also determined in the firing zone. Every clay deposit contains iron compounds. When those compounds are exposed to high temperatures in an oxidizing atmosphere, they react, and the products of that reaction determine the final color of the brick. Clay with a high iron content produces the deep reds and warm oranges that most people picture when they think of brick. Lower iron content or different firing conditions produce buff, cream, or pale yellow. The color of every brick is a direct record of the chemistry of the earth it came from. The third zone is the cooling zone. Bricks that exit the firing zone cannot be exposed to cold air immediately. The thermal shock would shatter them. The cooling zone draws fresh air in from the exit end of the kiln, which gradually reduces the brick temperature over several more hours. That air, heated by the still hot bricks, is routed back toward the preheating zone, completing the energy recovery loop that keeps the tunnel kiln running continuously. The entire journey through the kiln from entry to exit takes between 1 and 3 days. When the kiln cars finally emerge from the far end, the bricks on them are hard, dense, dimensionally stable, and colored by the ground they came from. Before any batch of bricks leaves the factory, samples are pulled for testing. The 3 standard checks are dimensional accuracy, compressive strength, and water absorption. Dimensional accuracy is measured with precision calipers, confirming that each brick falls within the tight tolerances required for consistent coursing in a finished wall. Even small variations in brick size accumulate across hundreds of courses and compromise the integrity and appearance of the structure. Compressive strength is tested by applying a hydraulic press to a sample brick until failure. The minimum acceptable result for a standard building brick is 10 megapascals of compressive force, sufficient to support the loads imposed by a multi-story structure. Engineering bricks used in more demanding applications such as foundations or retaining walls must meet significantly higher thresholds. Water absorption measures how readily a brick takes on moisture. A brick with excessive absorption is vulnerable to frost damage. Water that penetrates the material and then freezes will expand, causing the brick face to spall and crumble. Any brick that falls outside the acceptable range on any of these 3 tests is removed from the batch. The failed material is ground back into grog and recycled into the production stream at the beginning of the next run. Bricks that pass quality control move to the de-hacking stage, where robotic arms unload the fired bricks from the kiln cars and arrange them onto pallets in precisely organized stacks. The stacking pattern allows airflow between the bricks, prevents damage during transport, and produces a load that can be handled efficiently by forklifts on a building site. Once stacked, the pallets are bound with steel strapping and wrapped in plastic sheeting, protecting the bricks from moisture and debris during storage and transit. The wrapped pallet is a self-contained unit that can be broken down into smaller packages at the point of use. From the storage yard, the bricks are loaded onto delivery vehicles and dispatched. Most bricks are used within 500 kilometers of the factory that produced them. The weight of the finished product makes long-distance transport commercially unattractive. The brick that emerges from this process, fired, tested, wrapped, and delivered, is the product of a sequence that moves from raw earth to finished building material without interruption. Every stage is precisely controlled, every variable measured, and every substandard unit removed and recycled before it reaches a building site. Brick manufacturing takes place on every inhabited continent, and the scale of global production is difficult to comprehend. China is the world's largest producer, making more than 200 billion bricks every year. The pace of of urban construction in China over recent decades has driven demand that no other country approaches. India is the second largest producer, with annual output estimated at between 250 and 300 billion bricks, supported by over 180,000 brick kilns operating across the country. The United States produces approximately 7 billion bricks a year. In Europe, Germany, the United Kingdom, and the Netherlands lead production, with increasing focus on energy-efficient and lower carbon manufacturing as environmental standards tighten. In total, more than 1.5 trillion bricks are produced worldwide every year, more than 200 for every person on Earth. The raw material is abundant. The process is ancient. The product is unchanged in its essentials from the bricks that built the first permanent structures thousands of years ago. The next time you look at a brick wall, you are looking at compressed earth, fired in a tunnel at over 1,000 degrees, cooled, tested, and delivered to exactly where it was needed. Now you know everything that went into it.